18. For this reaction, so we have carbon 14 is being transformed, turned into nitrogen 14, right? Plus some random subatomic particle. Now, they're saying that if we have 100 grams of that carbon, and if that carbon reacts with, with whatever, right? If this carbon reacts, what volume of nitrogen gas, which is N2, is produced at 273 Kelvin and 1 atm. Okie dokie. All right. So to start this off, right, we do have some type of balanced equation. We have a carbon, and this is basically going to turn into a nitrogen, right? This is a nuclear reaction because we're only dealing with atoms at a time, no compounds here. Now, this is balanced. Generally, if you are dealing with nuclear reactions, for all your atoms, you're always going to have one carbon reacting with one nitrogen, and the rest will pick up the slack from your subatomic particles, whether you're emitting an alpha particle or a beta particle. So, in this case, we just have to go from the carbon to the nitrogen. Now, seems like they're starting us off with 100 grams of carbon, right? And at the end of the day, we need to find out a volume of nitrogen. If you're starting off with one substance and you're trying to go to another substance, ooh, this is going way back in the chem course. This is big bad stoichiometry, right? Where we're going to go from grams to moles to grams. So, in this case, right, if you have 100 grams, 100.0 grams of carbon, we can go to the moles of the carbon, and then from there, we can transfer over into the other nitrogen species here, which is moles of nitrogen. And then we'll take it from there, right? Because we need to find out N2. But at least from this equation, since it's just one carbon and one nitrogen, I can go from a moles of just C to a moles of just N. So that's the game plan for the first part of the question. But now, how do I go from grams to moles? Well, this is going all the way back, right? Anytime that you want to go from grams to moles, we can always just divide by the molar mass. But now the question here is, what molar mass am I going to use for a nuclear reaction equation? Well, they did tell us that we had carbon 14, right? And big number 14, the 14 on the top, C, and a 6 on the bottom, right? The 14 on the top indicates that you have 14 protons and neutrons. That's the atomic mass. 14 protons and neutrons. So some of you might say, hey, we could just divide by 14 because that's the molar mass. Now, let's maybe be a little bit more specific, right? If we know the total number of protons, neutrons, and electrons, we can get an even more definite mass for carbon 14. Because each proton, neutron, and electron has a little bit more mass than just one for protons and neutrons, and the electrons do give a little bit of mass. So the first thing that I'm going to do is just find out the exact mass. That's the molar mass that we're going to use. But if you want to use 14, that's fine. Let's just see how different your answer is compared to mine, if it really matters if we get the exact number. Now the bottom number here, 6, right? That's representative of the atomic number. That's just the number of protons. So if we have 14 protons and neutrons, and we got 6 just protons, I can take these two numbers and subtract them to get the number of neutrons. So we got 6 protons. 14 minus 6 is what? 8, right? I think. Yeah? 8 plus 2. Yep. So we got 8 neutrons. And then because this had no charge in the upper left-hand corner, I know that this atom is neutral, which means that all my positive protons have to equal my negative electrons because there's no charge difference. So if I have 6 protons, that means that I have to have 6 electrons coming in. So now, with each of these, I'm going to times it by the exact mass that each proton, neutron, and electron have. So I'm going to take my 6 protons and times them by 1.0073. I'm going to take my neutrons and times them by 1.0087. I'm going to take my 6 electrons and times them by 0.00055. Okay. So let's see. 6 times 1.0073. I get 6.0438. Okay, and then AMU. Let's do 8 times 1.0087. We get 8.0696 AMUs, and then 6 times 0.12355. 00055, enter. So just only a small amount is coming from the electrons. And now let's see what that exact mass is. We're going to add all these up. So this value plus this value plus that guy. So it's a little bit more than 14. So I got 14.1167 AMUs. Now just know that the AMU scale and the molar mass scale are the same values. One is just dealing with atoms, so really small microscopic scale. And if we want to say the same exact thing, we could bring it up to the bigger scale that we can see, which is the grams. So I can say 14.1167 AMUs, or I can say 14.1167 grams per mole. Same number, but one is just talking about the really small scale that we can't see. The other one is talking about the bigger scale, the gram scale, that we can see. So in this case, we're going to take our 100 grams of carbon. Maybe I'll put that in red. And if we wanted to do it the dimensional analysis way, right, times by the ratio, grams of the carbon go on the bottom, the moles of the carbon go up on top. And now, for these grams per mole, right, it's 14.1167 grams goes on the bottom for every 1 mole. And that's why it's just divided by the molar mass, divided by that 14. Grams of carbon gets canceled out, and we are left with just the moles of the carbon. So we're here now. Now, don't stop, keep going, trust the process, right? Now we want to do my next dimensional analysis to go from moles of carbon to moles of nitrogen. This is using the balanced equation. So anytime that you're changing over from one thing to another, it's always through moles, and it's always using some type of mole ratio, whether it's the balanced equation or your coefficients. But let's see here. So now I'm going to put mole of carbon on the bottom, and I want the mole of nitrogen going up on the top. Now we use those ratios. But just as we said before, for every 1 carbon, we have 1 nitrogen. So we got 1 mole of nitrogen for every, maybe I'll do it in black, 1 mole of nitrogen for every 1 mole of carbon. So the unit, or the numbers, are the same. And now you're just left with moles of nitrogen. So let's see what we got going on here. So all we got to do is just 100 divided by this number. Okay, so we got 7.0838 moles of just N. Now, pause the video if you need to. We don't need this anymore. This is the most important part that we just found out. We know that we have a total of 7.0838 moles of just the nitrogen. So pause the video. Maybe I'll just get rid of all this stuff. Say goodbye. And this we don't need anymore. So this goes bye-bye. But now we need to transfer over to N2. But in every one N2, how many nitrogens do you have, right? One N2 is the same as saying 2 nitrogens, right? If I have one of these, one whole compound, this is the same as saying I just have 2 nitrogens. So if we have 7.0838 moles of nitrogen, what am I going to have to do to just find out N2? Well, let's see. We could do dimensional analysis again. We can say 7.0838 moles of nitrogen times by that ratio. Mole of nitrogen goes on the bottom because you don't want just nitrogen. You want the N2 because that's what the question's asking for. But in every one whole N2, you have 2 nitrogens. So I have to take this value and just divide it by 2. And now I have the moles of N2. So let's see. I'm just going to take the whole number here and just divide by 2. Beautiful. So now I have 3.5419 moles of N2. Okay. Now, let's group together all the information that we know. We now have a mole value of N2. So we have 3.5419 moles of N2. They gave us a temperature, right, which is a T value. So I have a T value of 273 Kelvin. They gave me a pressure, so I have a P value of 1 atm. A mole value is a N, right? And we're looking for a volume, which is a V. Any formulas ringing a bell? We got a P, V, we have an N, T. We only have one of each. Oh, isn't that the formula? PV equals nRT. It most certainly is. So what I'm going to do is I'm just going to bring this up. There we go. Okay. Because I have my pressure, 1 atm, and it's in the correct unit. If I'm searching for the volume, which is what I'm searching for here, the volume has to be in liters. The N value is the moles, and we have that, 3.5419 moles of N2. The R value is the constant value, the constant gas value, right? Constant. And that's 0.08206, or you could do 0.0821. That has all the units in there to make those units specific. So atm times liters over mole times Kelvin. So that means that the temp has to be in Kelvin, but that's all good because we have 273 Kelvin. So now let's just get down to it. 1 times my volume equals 3.5419 times 0.08206 times 273. 1 is just times by itself, right? So whatever I'm going to be doing now, that's going to be the answer. X equals, I'm going to take the full amount here, times by 0.08206, times by 273. And I'm just making sure that I plugged everything in. Looks good to me. 0.0827. Okay. There we go. So 79 point, I guess we'll do 4, I guess 3 sig figs. It doesn't really matter. Does anyone care at the moment? No. 79.3 liters. And that is the volume. Wowsies. I hope this helped. So for 100 grams, you need a large container. But that makes sense. I mean, combustible, not even combustible, but nuclear and unstable reactions would require a big vessel to carry because they're going to produce a lot of energy. So the numbers make sense. 100 grams for 79 liters. Okay, I'll take it. I hope this helped. Let me know in the comments. Thank you so much for viewing the video. Subscribe to the channel. And I look forward to helping you with more questions. We also opened memberships for the new school year. If you guys want to help us out a little bit more, we would greatly appreciate that. We got tons more coming your way this school year. And go check the channel out. We got physics, we got math videos, chem videos, obviously. And yeah, keep studying hard. We're rooting for you guys. And I hope you have a great day. Bye-bye.